Hello, and welcome to my third instructional video concerning the use of the thin lens and magnification equations for the grade 10 academic science program in the optics strand, Ontario, Canada. If by chance you are not a student in Ontario, but instead in another province, or perhaps in a state in the United States or another country, it is hoped this video will still be of some benefit and help to you, because perhaps you are studying optics in grade 11 physics or perhaps in grade 9 science as well. And so the hope is that you will be able to be proficient in and interpret the results of the thin lens equations. In this particular case, unlike my previous video, I've chosen a diverging lens, a lens that is somewhat shaped like an hourglass, and this lens has the effect on light to diverge the rays of light. And so there can be no real focal point. The focal point is defined to be virtual, or said to be virtual. And as a result, the focal length, by convention, will have a negative sign attached to it. This is very important for doing the mathematics, making sure that you have the correct integers to go with the mathematics. In this case, I'm just going to arbitrarily choose a focal length for this lens of 7.1 centimeters. I believe that is the same focal length from the last video. The focal length, remember, is measured from the optic axis, this vertical axis, to the focal point. And recall that this is a virtual focal point, and thus this will be a negative number when used with the thin lens equation. I'm also going to choose an object whose distance is roughly double the focal length, so somewhere in the neighborhood of 14 centimeters. This is the height of the object, and the distance of the object to the center of the lens, d sub O, will be 14.0 centimeters. This type of lens goes by a variety of different names. It's a concave shaped lens, as given by the sort of caved in nature here. It's also referred to as a diverging lens because it causes light rays that come out of this side to be divergent. And it's also referred to as a negative lens due to the fact that the focal length is considered to be negative. Okay, so let's have a look at the mathematics here, how we're going to solve this and interpret the results of this situation. Once again, we're going to begin with if I do, I die, which is just a little memory aid for this particular equation. If, I think you can figure this out, I do, I die. And as I've told my students, this is the topic sentence, similar to a topic sentence one would have in a paragraph that you're writing in language arts or English. And I always have my students begin with the topic sentence. From this point, they can then do some algebraic manipulation to determine one of the unknowns. In this case, we are going to be looking for the distance to the image. So I want to isolate this particular variable here, or this term here, 1 over di. In order to isolate it, I must remove 1 over do. However, as you have learned in math, you can't simply just erase this term. You must subtract 1 over do from this side, like so. And what I do to one side of the equation, I must also do to the other to preserve the equality. 1 over do minus 1 over do is 0. This cancels out, and I successfully isolated 1 over di. By simplifying and rearranging, I end up with an equation that we can solve in terms of 1 over di, or the reciprocal, and that will be equal to 1 over f minus 1 over d sub O. So now it is a matter of solving for the unknown. We keep our equal signs all lined up vertically. It's very important to have a well-organized area that you are working in. It's not chaotic. It's very easy to understand the flow as you work down the page. So the important thing to remember here is that my focal length is negative. And so this term will become negative 1 over 7.1 centimeters. And what I will do is simply place brackets around this term to keep the negative sign as part of this, and I'll subtract from this 1 over the distance to the object. The distance to the object is 14.0 centimeters. Aligning our equal signs vertically, we then take the reciprocal of each of these terms. The reciprocal is this button on your calculator. Alternatively, depending upon the manufacturer of your calculator, you may see this term, x raised to the exponent -1. These two are synonymous, as you may remember from grade 9 math. To determine the reciprocal of 7.1, I would enter in my calculator 7.1 on the screen like so, and then I press the reciprocal key button, and the reciprocal of 7.1 comes out to be 0.1408 with a number of other digits after that. I have to remember to keep my negative sign because it is a virtual focal point, and all virtual objects or items in diverging lenses or converging lenses are addressed with a negative sign. So if I have negative 0.1408, remember you must have a unit that goes with the number, otherwise the number portion is rather meaningless. And I want to subtract from that 1 over 14.0. In this case then, I would do the same thing as before. I would simply enter into the calculator, and you can try this. Hopefully you are trying this as we are doing this. You will simply hit the 14.0, and on your screen you will see 14.0. Then you will once again press the 1 over x or the reciprocal key button, and you will be left with 0.07143 with other digits perhaps after the 3. This is enough precision for what we're doing. Once again, we transfer that number to here, remembering that all numbers require a unit. And now it is merely a matter of subtracting these two, and when I take negative 0.1408 centimeters and I subtract from it a smaller number, 0.07143 centimeters, I am still left with a negative number, and that negative number is 0.2122 centimeters. It is, of course, important to remember that what we have just calculated is still 1 over di. I'm not interested in the reciprocal of di. I am instead interested in the distance to the image, not 1 over the distance to the image. And so if I take the reciprocal of this by flipping, then I must take the reciprocal of this number. And once again, I can do that by entering into my calculator 0.2122, once again for the final time, pressing the reciprocal button. And when I press the reciprocal button, I find out that the reciprocal, or inverse if you want to think of it that way, is 0.2122 centimeters is negative 4.71 centimeters taken to 2 decimal places of precision. So now, through a mathematical process, we have successfully determined the distance that the image would be from the optic axis of that diverging lens. And in fact, if we measured that on a ray diagram, we should get something very close to 4.71 centimeters, remembering that the negative sign simply means that the image lies on the same side as the original object, and hence it is virtual. The second step in this process is to determine the magnification of this particular image relative to the original object. And once again, we start out by writing the topic sentence or the main equation. The magnification equation is equal to actually two ratios that come about from the ray diagram because they are the sides of two similar triangles. The height of the image as a ratio to the height of the object is equal to negative the distance to the image divided by the distance to the object. In this case, we do not have any data concerning the heights of either the image or the object, so this is not of use to us, and instead we will look at this form of the equation. Once again, we replace our known values with our quantity symbols. Remember the negative sign, that's important. And we look at what is the distance to the image. Well, the distance to the image from before was negative 4.71 centimeters. And that is divided by the distance to the object, positive 14.0 centimeters. The positive sign indicates that the object is a real object. The negative sign attached to the image distance indicates to you that it is a virtual image. We will place brackets around this term for good form, equal signs lined up, negative, and I will do this division, and when I do this division I come out with negative 0.34 to two decimal places. A negative times a negative, as you may recall, yields a positive. And so I have successfully calculated the magnification of that image relative to the object. What does this mean? What is an interpretation of this result? Well, perhaps you can take a few seconds to think about why this is a decimal and what this positive sign might mean, especially if you've already seen the second video dealing with a converging lens. Well, hopefully you've successfully come up with the fact that because this is a decimal, that the image is going to be smaller than the object. If this is the original object, then the image will be roughly 1/3, quite 1/3, but get the idea, of the original object. The positive sign simply gives you an idea whether or not the image is upright or inverted relative to the original attitude of the object. Because this is the positive sign, I've drawn my image pointing up in the same sense and same attitude as the original object. So, if we take a look at the thin lens equation and the results of the magnification equation, we can begin to, we can complete our properties of the image by looking at size, attitude, location, and height. The size is smaller. The attitude is the same as the original. The location of the image is 4.71 centimeters. 4.71 centimeters from the optic center, and the type of image is virtual as given by the negative sign that is attached to the distance to the image. So there you have it, the thin lens equation for a diverging lens and the magnification equation of a diverging lens. In all cases, diverging lenses always yield images that are upright, virtual, smaller, and they're all located on the same side as the original object was. I want to thank you all very much for watching this. I do hope that it has been of benefit to you and that you feel more confident in your ability to work with the thin lens equations. Please don't be afraid of them. It is not that difficult. It's just a matter of being organized and following a method, and unless some silly error occurs, you will always get the answer correct. Enjoy, have fun. Thank you.